Yeah, hi and good morning or good afternoon, wherever you may be and all that. I would like to actually walk you through our work on distributed dynamic allocation in 6G INS subnetworks for industrial automation. This is a joint work between researchers at Aalborg University and Nokia Bell Labs here in Aalborg. So here is an outline of the talk. I would start with some introduction and trying to actually showcase our 6G INS subnetworks with requirements and some initial designs. I would also introduce the dynamic channel allocation algorithms that we have evaluated. I would then discuss the performance evaluation results before going on to actually conclude the talk. To start with, I would like to actually mention that the term subnetworks here is actually used to refer to low power, short range cells, which are actually expected to overload, offload demanding services with extreme requirement. For example, below 0.1 milliseconds communication loop with a wire-like reliability from traditional micro or macro networks. So these subnetworks should be able to actually provide the required extreme service level at any location, wherever they may actually place at any given time instance. We actually foresee this type of subnetworks to be very to actually provide the opportunity to start to think of trying to actually remove the last cables in industrial control. For example, cabling that actually control the arms of a robot and all that with wireless networks. And this definitely would actually require much lower latency than what can be supported by the current 5G NR radio networks. This type of subnetworks could also be used, could also be actually installed inside vehicles. So here, this could be for things like ABS or AMBOS and all that life critical application. Another application could also be for deployment for in-body network, for example, for a wireless heart pacemaker. And this, again, is a life critical condition that would actually require some level of guarantee of the low communication loop and extreme reliability requirement. In summary, here are the KPIs that we have actually set. So we have the communication loop, which has to be below this latency requirement. And we would also like to have reliability measured in terms of the probability of outage below 1 E minus 6 and then again here we need to be able to actually guarantee this at any given location or and time. So for this, we have used what we actually call the probability of failure as a measure of the spatial availability of the services within each subnetwork, and that is actually measured as the probability that a particular control loop will fail to meet the latency and reliability requirements. So here is basically a summary of our initial or current design concept. Essentially, we have looked at a 3D frame with OFDM waveform. We have scalable frame size, as we also have in 5G NR, but with maximum duration, which has to be lower than the 0.1 milliseconds requirement. We would also expect that given the short cycle time, we would need to have large bandwidth. Here is just an illustration of the frame structure with transmission from each devices being actually repeated blindly by hopping over multiple channels. Right. Now I will introduce the dynamic allocation algorithms, which essentially what we are doing here, we have subnetworks, which could be robots or vehicles actually moving around. Within each subnetwork, we have a controller which actually takes measurement from the sensor to generate corresponding control actions to the actuators and all that. And all this actually moves, and it needs to share radio resources. Essentially here we have time frequency resources. So which frequency band should I use to transmit within a particular subnetwork at a given time, such that I would be able to actually meet my extreme requirement. So to do that, we have actually assumed that we have a total bandwidth of a B, which is actually partitioned into a number of channels with BCH as the size, and all the channels are then grouped into a number of groups. Here in this illustration here, we have 4 groups. So the assumption here is that the total number of channels within each group is at least greater than the number of repetitions required within a subnetwork. We can then actually restrict transmission within a subnetwork to a channel group, and the subnetwork only initiates switching to another group when the condition becomes bad. So the task now is how to have algorithm for enabling this monitoring the frequency channels and initiating switching decisions based on the sensing measurement at a given time. So to do that, we have looked at a number of distributed algorithms, including what is called the epsilon greedy, minimum SINR guarantee, and the nearest neighbor conflict avoidance. The assumption here is that the controller at each subnetwork, which we could also see as an access point here, actually acts as the processing unit, which actually continuously monitors the worst case SINR on all the channels within the subnetwork, and also is able to listen and collect measurement of the interference power on all other channels. So based on this knowledge, it can then actually initiate to a switching condition when the worst case SINR starts to go below the target SINR to guarantee the latency and reliability requirement for the control loops. So here is the list of algorithms that we have looked at. The first class is what we call the epsilon greedy algorithms, where essentially when you actually notice that the SINR on the occupied group is going below the desired SNR, you will either actually choose randomly or greedily with some probability, epsilon. While the greedy case corresponds to a best effort case where each subnetwork actually just greedily chooses a channel which could be even much better than what is required. To ameliorate the challenges that such behavior may actually introduce, we have also looked at what is called the minimum SINR guarantee. And as the name actually implies, essentially what we do here is to say, okay, I am not going to select the best, I would only select the worst, which means my requirement. And if there is none, I just choose the best. And then on top of that, we have NNCA, which basically relies on the assumption that each subnetwork is able to explicitly identify the channel group occupied by its neighbor, its nearest neighbors, or the strongest interference. And as such, it could essentially avoid using the same channel group with its nearest neighbor, where K here is the number of channel group. And as a baseline, we have also looked at the centralized graph coloring, where we apply the greedy algorithm to the interference matrix at any given time. Right. So I would show some evaluation results where we have a number of subnetworks moving at a given speed and all that. So the shadowing and path loss is actually calculated using the following model. So we have actually ensured that we have a spatial and temporal related shadowing by using this notion of Gaussian random field. Now here we actually try to find what is the optimal configuration for a transmission. Do we have more groups and have less repetitions, and what we actually observe here is that with 6 channel groups and 2 repetitions, it seems to be the best that we can actually achieve for the particular use case we have looked at. Now comparing the algorithms, what we see here is that here is the random and here is the best case algorithm, which is the NNCA and the CGC. And what we see, if we look at the PLF to a target of 1E minus 6, we see a drastic decrease in the amount of bandwidth required to support such requirement. However, of course, the NNCA requires additional information, which is actually a part of the focus of our current research on protocol designs for subnetwork identification. As a measure of the overhead, for example, the amount of radio resources for enabling communication of information about switching. We also looked at the switching overhead, which is basically the ratio of the amount of time where a switching is performed to the total number of time instant. And what we can see here is that the NNCA again has the lowest switching rate. So which means that if we have this additional information, then we can achieve reasonable performance and a drastic improvement in bandwidth requirement at very low switching rate. So what does this actually translate to? If we look at here we have just tried to actually calculate the estimated bandwidth required to support the 1E minus 6 outage up to 1E minus 4 or 1E minus 6 PLF within the 0.1 milliseconds cycle loop. What we can see is if we compare the centralized graph coloring or NNCA with the case where we don't have grouping or even the random selection algorithm, what we see is a drastic improvement or decrease in the bandwidth requirement. For example, here we can see that we can scale the bandwidth from around 4 gigahertz to below 2 gigahertz. To wrap up, we have shown some algorithm for distributed allocation of resources in 6G in shared subnetworks. The algorithms are actually simple and only relies on the measurement of SINR and interference power, and our simulation studies have shown great potential for improving the performance of these autonomous shared subnetwork and also reducing the resource requirement. Our current research is on machine learning methods for actually introducing some level of intelligence into these subnetworks. Thank you very much. And thank you.